Good afternoon. Welcome to the Oxford Martin School. We're very pleased to have Vlatko Vedral here today. Vlatko is Professor of Quantum Information Science here at the university. He's an old friend of the Oxford Martin School, having been a director of our Oxford Martin program on bio-inspired quantum technologies, which ran for 7 years, I believe. He's published hundreds of research papers on various topics in quantum physics and quantum computing. He's been awarded a number of international prizes, among them the Royal Society Wolfson Research Merit Award, the World Scientific Medal in Singapore, and the Marko Jaric Award in his native Serbia. He's also active beyond the specialist world of quantum physics. He works, for example, with the World Economic Forum on the future of computation, and he's a passionate communicator, keen to share his sense of wonder and excitement at the big questions of his field. So in this guise, he is the author not just of 4 textbooks, but of 3 popular books, of which Portals to a New Reality is the latest. Just to flesh out that quick portrait, according to the publisher's blurb, when not studying the fundamental nature of reality, Vlatko enjoys drawing, wakeboarding, and playing his electric guitar very loudly. So, Vlatko, if you could come up and tell us more about your book. Thank you.
It's a great pleasure. Thank you. Thanks. Thank you. Thank you. And thank you for coming here to listen to fundamental science. I think it's something that doesn't probably receive as much interest these days when we all read about quantum technologies. But I think the interesting point is that these quantum technologies are now reaching the level where we can focus them back to probe some of the ideas in physics, and that's where I come from and what excites me. The Martin School is, as Julian said, it's a perfect venue for this, because one of the chapters is even based on the work that started here. And there's an even more personal connection that I had many discussions with Jim Martin himself. There's even a transcript of an interview, I think, where he interviewed me about this picture of the world where everything is quantum, that the whole universe is quantum. And I think he shared this belief that this is the right way to think about reality. And that's what I would like to communicate to you today. And of course, I will be here to answer any questions, any other details I describe in the book, and obviously feel free to contact me outside of that, because I don't think I managed to explain things in enough detail, even in the book, obviously. So that's the summary here, that if you almost open a random discussion online about physics, you will hear something like physics has been stuck for 100 years. There is no new theory. We've had these 2 theories, general relativity, the theory of gravity, Einstein's, and quantum physics, and they're perfectly good in their own domain. 150 years of no conflict with any of the experiments, but we have no way of testing them together. We don't really know how to unify them, and people feel that physics is stuck. And the way I rationalize this in my book is that there was a genuine question of not having experiments that are sophisticated enough. But I think there is a slightly more subjective angle to that, and that's what I want to tell you about as well, is that for a long time we've been stuck with the wrong view of quantum mechanics, actually. So that's the second thesis, and in fact, the first portal that I will tell you about, I will kind of go very briefly through these 5 experiments that I think we are now on the brink of being able to execute, which I think will ultimately really lead us to new physics. So actually, I disagree with all of these statements that physics is becoming boring. It's never been as exciting as now, I think is the way I would put it. And that's what prompted me to write the book, really, to communicate this fact, which I don't think is out there. Not many people are saying that. So probably the most dominant view of quantum mechanics that you've heard about, and I think that's what also prevents us from unifying or quantizing gravity, if you like, is the Copenhagen interpretation. And I'm going to go against it here. And there are two reasons why I'm going against this. Copenhagen view would say something like this. It's okay that the micro world is very weird and quantum systems really can be in a superposition. They can be in many different places at the same time, the famous quantum superposition property. However, when we, classical objects, according to this view, interact with these systems, then we get classical information out and we can communicate that and everything is okay. That was kind of, I'm caricaturing a little bit the view, but I think that's what Niels Bohr was all about. And given that he was from Denmark, you know, that's the kind of Copenhagen interpretation. Now, it seems to me that the last 100 years, especially the last 20 years of quantum mechanics going into a bigger and bigger macro domain, are telling us the exact opposite to that. In fact, there isn't a classical world. It's just that beyond certain, let's say, macroscopicity, beyond certain size of a system, it's currently difficult for us to reveal quantum properties of these systems. So the right way to put it is that they're hidden. It's not that they are collapsing or they are vanishing, they are destroyed. They're simply hidden in the noise of these large systems, which comes from all sorts of other sources. So that's basically, I think, the only consistent. Experiments certainly back this view up, but even more so, and I think this is what many people are not aware of, this is the only consistent way to account for everything. And the claim in the book, I wrote the book deliberately in a slightly combative way. This is important to understand that actually the only consistent way to do this is really to treat everything quantum. As soon as you divide the universe and you say half of it is classical and the other half is quantum, you run into all sorts of paradoxes. And my claim is that every time you hear paradox in quantum mechanics, the only reason there is a paradox is because someone made a mistake to classicalize something they shouldn't be classicalizing. So that's the idea of the book. And ultimately, it is a very weird picture of reality. So I'm saying it's all a quantum wave in the sense that it obeys sets of equations that really look like wave equations, just as you would expect a water wave is doing. However, the key difference, and this is what stretches our imagination, is that these waves, you would normally talk about the height of the wave. If you stand in one point, you would be looking at how high the water wave is, and it's going to go up and down in time, and that's a single number quantifying the height. What Heisenberg did exactly 100 years ago, the first paper, the paper we believe starts the whole thing, is he said you can't think of quantum things as classical numbers. You have to upgrade them into what Dirac later called Q numbers, quantum numbers. Now, why this stretches our imagination is because in this case, they happen to be huge tables of numbers. They are matrices, as they are formally known, and they happen to be ultimately infinity there are infinitely many rows of this Q number and infinitely many columns. And to every classical property, the position of a particle, the momentum, the energy, you name it, anything you know pertains to a particle or a wave in classical physics, in quantum mechanics, it becomes a Q number. And if you acknowledge that, there are no paradoxes. You suddenly have no measurement problems, you have no discontinuities or anything else, and that's the beauty of that. So let me spend a little bit of time. There were lots of discussions in the early days, incidentally, and I think this maybe illustrates best this key message. There were lots of discussions along the following lines. If you claim that everything is a quantum wave, then if you take decay of a large nucleus, so you take a you take a large nucleus, you have a radioactive decay, which happens to eject what we call an alpha particle, but it's like the helium, the nucleus of the helium atom. So you eject 2 protons and 2 neutrons. And in the 20s, 30s as well, this technology developed the cloud chambers. So basically you have a dense cloud of molecules in which this takes place. And as this alpha particle gets emitted, it starts to ionize the molecules in this gas, and you see this vapor which leaves a trajectory. So each of these trajectories is a separate run of the emission of this alpha particle. And the big mystery was, if Heisenberg, Dirac, Schrödinger, and all of these people claim that particles are really quantum waves, why does it take a straight line trajectory as it would in Newtonian physics? This was a big discussion. In all these, there was a famous Solvay meeting in 1927 where people discussed this. There were many arguments between people, and various people settled this ultimately. I think the people I mentioned, so, you know, why doesn't it look like this? That was the question. If you really claim it's a wave, why doesn't a particle leave ripples of this kind? And so various people explained this. I'm kind of listing some of them. Heisenberg certainly was maybe the first person to explain it. Darwin, this was Charles Darwin, not the Charles Darwin, but the grandson of Darwin. It's one of those families like Huxley's. There are many, or Bernoulli's, many famous people in there. And he was a fantastic quantum physicist. Mott, another one from Cambridge as well, and later even Schrödinger. And this is not much known, that ultimately even Schrödinger subscribed to this picture, and I will tell you that in a second. So basically, how did they explain that? They explained it by simply saying that every time you have an emission of this alpha particle, it indeed is a wave. It's a spherically symmetric quantum wave in all directions. But the first time you ionize a molecule here, that acts like a measurement, as we would call it. And then you can calculate the probability that the next molecule you hit lies along the straight line. And actually the probability becomes very large that this is the case, especially if the gas is very dense and these collisions are very close to one another. So what happens in the quantum world is that the particle starts to spread. That was the way Heisenberg explained it. But as soon as it hits the first molecule, this molecule localizes the position of the particle to a very small range of possibilities. And then the particle continues to spread, but it hits the next molecule here. So yes, it does behave quantumly in between, if you like, but it's intercepted by a sequence of measurements. And then what Mott did, really, is he said you should think about the gas around also as made up of quantum systems. So this is the thing I emphasize leads us to make lots of mistakes, that you should think of the gas as a bunch of classical atoms. No, they are also underpinned by these Q numbers, which leads us to an amazing conclusion, which is that each of these trajectories gets taken simultaneously. So you get a molecule excited here and subsequently the one here in one branch, as we call it formally, of the superposition. But you also at the same time have a branch going this way and a branch going that way and so on. So this is the full quantum reality. So it's not that anything collapses when you have a measurement here. What it does is it maybe makes this trajectory narrower, is what Heisenberg would say, but actually it doesn't eliminate all of these other trajectories. And that's the full picture. If you really admit that all of these things, including the molecules in the gas, are quantum mechanical, then you get this superposition that starts with the alpha particle, gets imprinted on the gas, and ultimately it spreads out. And that's how Mott explained this. And I like this picture, that everything is made of Q numbers, because I think people who say that when you make a measurement, you collapse the quantum superposition, according to this logic, are deeply mistaken. And then I'll give you a metaphor how they are mistaken. Imagine you have a die. It's a bit like a Q number, a metaphor for a Q number. You roll this die, and you observe number 5 on the top surface. Now, no one in their right mind would say that the other 5 numbers have disappeared from this die. It's just not, you're not looking at it from above. But there are other observers, if you like to call them. I'll argue against observers as well. But there are other observers who, of course, see all of the other numbers as well. It's not that you eliminate them. You can actually experimentally probe subsequently whether these other properties exist at the same time. So this is not, in a way, just an interpretation, if you like. You can verify, at least up to some degree of complexity, lots of these statements. So yes, it is a weird reality, but once you really acknowledge that everything is weird in the same way, that's the way that Feynman kept saying, you know, we've got this weird double slit experiment, but once you acknowledge that the rest of it is weird in the same way, then we're all okay. At least, you know, the weirdness is coherent in the universe. There are no different kinds of weirdnesses. So here is the 5 portals, and I will, like I said, I will take you very superficially and very quickly through this. But to me, this kind of view is the one that first I would like to test. So that's going to be the first portal. And the point I'm making there is that it seems to me that it's a mistake. And I know that most physicists, you would even hear various physicists saying, making comments like, I'm repelled by quantum mechanics because it seems to insist that observers are crucial. And frequently you will hear some new age sounding statement like you create your own reality by looking at it and stuff like that. That's not the picture that I'm advocating here, actually. The picture is even weirder in some sense than this kind of logic. So I'm kind of upping it. I'm trying to promote an interpretation that I think is certainly beautiful, but even more unusual. And then I'm going in the direction of testing really time. I singled out time because I think rather than looking at gravity as space-time, I think we physicists argue a lot about time, the arrow of time. Is time really a fundamental property, or is this some emergent thing and stuff like that? So I will take you through this. I start the book by making this statement about Kelvin. At the turn of the last century, 1900, Lord Kelvin was asked to give an address at the Royal Society about the state of physics at that time. And this gets frequently quoted, that he said, it seems everything is okay, but we have these 2 clouds on the horizon. And actually, he was really spot on that, of course, one of the clouds turned out to be relativity, Einstein's relativity, which came 5 years later, and the other cloud was quantum mechanics, which basically started round about the same time. In fact, Planck wrote his paper in the same year when Kelvin gave this address. So I would like to say that somehow we do have places where we think something could go wrong with the theories we have now. They're certainly worth testing, and you can also tell that it's worth doing that because most of us in the physics community don't even agree on what the outcomes of these experiments would be. So as soon as you hear that there is a controversy of this kind, that must be the thing to actually look at experimentally. That's the best indicator that these are interesting questions. So this portal 1 argues that it's a mistake to say that observers are crucial, that quantum things only become real when an observer witnesses this. You will hear a lot of these statements of the Bishop Berkeley kind, right? That, you know, if a tree falls in a forest and there is no one to observe it, you know, did it really fall or make a sound or whatever he was speculating as an idealist. You hear lots of statements like this. And the statement I used in my book is the reverse. I think quantum mechanics is the opposite of Bishop Berkeley, which says the universe exists in its totality only when you don't observe it. It's the opposite. It's not that it becomes real when you observe it, but it's only real when you don't observe it. And I can explain what I have in mind by that as well. It's a direct consequence of the Q numbers, basically representing everything, including the states of our brain, let's say. That's a big hypothesis. We have no idea how our consciousness works, but at present we have no reason not to apply the same methodology to this. So basically, according to this, and I'm almost quoting Schrödinger directly, measurement is just the creation of entanglement between the system and the observer. And the beautiful thing about this is that the two are completely interchangeable. When two things get entangled, it's a symmetric property. When I look at a simple atom and entangle myself to this atom, you could equally well say that the atom is observing my state, and that you're not making any mistake if you say something like that. So an observer is simply another physical system that doesn't need extra properties other than enough of these Q numbers, enough capacity, if you like, to handle all of the entanglements that you need. And that's interesting. Schrödinger was, most of you would be familiar with Schrödinger's cat. And in 1935, he wrote this paper saying, if you think that microscopic superpositions are weird, then I will tell you that as soon as these microsystems couple to large systems, it's going to be again superpositions at a much larger scale. And now what? And I think initially the feeling was that he thought this was absurd. But a few decades ago, a set of lectures was discovered that Schrödinger gave few years before he died, Dublin, I think it was 1951, 1952, where he's quite cautious. The introduction says, I'm going to tell you something that may lead you to think that I'm completely crazy and you will want to lock me up. But actually, what I wrote in this paper, Schrödinger's cat, I think that's what it's like. That's the only consistent picture. It really is like that. And that's interesting. And many physicists have reached this. I'm not the only one advocating this, obviously, but there are many other views as well, and that's why it's interesting to test these things. So he said, this way you have no collapses, no quantum jumps, no discontinuities, no spooky action at the distance, and so on. He made some very strong statements. You know, he said if quantum jumps turn out to be real, then I'd much rather be a plumber than a physicist. And I think this shows you already how much the story that we tell ourselves matters to us. It really is about understanding reality. Reality I'm not arguing again, I'm arguing exactly that quantum reality is the way to go, and it's different to classical reality, but I certainly would not argue against reality, which is what you have in many of these other versions and interpretations. So that's kind of the portal number one. Portal number two, very briefly, talks about special relativity and testing quantum mechanics at the interface of special relativity. So in special relativity, you have this famous twin paradox where one twin stays on Earth, another one goes on a journey, and I think you've all seen movies like Interstellar and all of these other ones that basically relativity tells us that different speeds, in a way, or again, you know, the word we use is observers, but there is nothing fundamental. You can say different atoms moving in different ways will experience different times. And so what I'm proposing is to do that with a single quantum system. So that's the beauty of quantum superposition. A particle can be its own twin. You don't really need twins here. So you make a superposition of a particle. In one of these locations, you take that particle on a journey and back. And now the weird thing that relativity says is you brought it back to one and the same particle in the same location, but there is a superposition of a younger version and an older version of this particle. That's mind-blowing. By the way, we have atomic clocks that could do this kind of experiment. This is why I keep saying that we are on the verge of testing some of these interesting things. And it makes you think immediately, what does time even mean in this case? What time is it as far as the particle is concerned? If it's, and just listen to my language, how bad it is, the classical language. It's in a superposition of two different times at the same time. What time are you talking about? Do you see what I mean? And I think that was frequently a point that Heisenberg made. We need to purge even our language of these classical notions. You're never going to basically understand the quantum reality properly if you keep describing it in terms of classical information. It just isn't classical. It's just that's as simple as that. And you can have weird things that I'm saying in the last statement. You can actually have a superposition of a particle evolving forward in time and backward in time. So what does that mean now? How can I have two opposing arrows of time simultaneously? It's really weird. Is it like that? I'm not saying, I have actually no idea how these experiments will come out ultimately, but certainly I think they're interesting to contemplate. And then I think what I did later, again, I don't want to talk maybe too much about all of this, but let me take you to the key part of this portal 3. So after investigating the interface between quantum mechanics and time, what I went on to ask is, what about gravity? And I think many people would say this is the biggest outstanding problem in physics. And if you ask a lot of physicists where they think quantum physics could go wrong, this is certainly the place in physics where something interesting could happen. And no one really knows. And we haven't really probed it at any level. Forget about black holes and very strong gravity. The point that I'm making here, and it's based on a couple of papers that I published with Chiara Marletto and Sugato Bose published with his own team a few years back, which was to say, why don't we even test this in the limit of low energy, which means gravity is very weak. It's Newtonian to a first approximation. You can even do it classically the way that Newton did it. But use a superposition principle. Put two masses into two places each, and now ask what happens with gravity. So people who claim that gravity collapses quantum mechanics would say, well, gravity will only actualize one of these positions. It's going to collapse it into one of them and then just apply the usual gravity. Whereas if you believe that gravity is quantum, and that's why this happens to be a good test of that, it would actually entangle these two masses because it would simultaneously act between all of these elements of the superposition. And by the way, if you think this is weird, then you shouldn't, because electromagnetism already works this way. If you put two electrons in the equivalent superposition, then electromagnetic field would exactly act between all of these positions simultaneously. And we actually know that. That's been done experimentally. So it's beyond doubt that all other fields, if you like, are already quantum mechanical, but we don't know that for gravity. Depending on who you talk to, some experimentalists are, I think, extremely optimistic. I tend to be an optimistic person as well. I would say within 5 years, we would know something like this. Some people are saying maybe 10 years. But we certainly have the right technology in quantum technologies to embark on this. And if you did get quantum entanglement, the exciting thing is that this would be the first known violation of general relativity, classical. It's the first violation that you can't just do it classically. To me, that sounds great. At least you've eliminated half of the community, or the ideas from half of the community, who claim that gravity can be classical. I think it's important. Still don't know how to proceed after that, so I think it's still an exciting, so that's a kind of a picture of two massive interferometers and then letting these guys couple through gravity. And all of these ideas, I should say, go back to Schrödinger, who really envisaged, if you have a radioactive decay and you have a particle in two places at the same time, then you should really follow simultaneously what it does in each of these places. So in one place, he imagined a bottle with poison, the particle hits the bottle, breaks it, the poison is out. The other one, nothing happens, but it's simultaneous, both just like the alpha particle experiment. And then it's put this cat in the box, as you know. In one case, the cat is dead, in the other one is alive, and so on. But here, luckily, we don't have to experiment with anything as complicated as this. We are basically doing the same experiment. But all experiments, by the way, in quantum mechanics are variants of Schrödinger's cat experiment. That's maybe the best way. That's the central mystery of quantum mechanics, if you like. And then so I think this is one of the last bits that I will comment on, and it's particularly nice to be here, like I said, because Jim and the Martin School funded a lot of these experiments to go really in the direction of living systems. So if you brought this picture up to this level, then the question is, what is it that's really preventing us from creating a quantum entangled state between two living systems? Why not? Why can't you at least take simple degrees of freedom of two bacteria, control them in as best as you can to eliminate all sorts of other noises, and the question is, will they become quantum entangled? And that sounds mind-blowing. That really does sound mind-blowing to me. We are not there yet, but like I said, I wouldn't be surprised again if within the next decade or so we have an answer to this. And people always get, when I talk about this, people get the wrong impression that, yes, I'm betting that quantum mechanics will pass all of these tests. That's kind of my intuition. But I would be even happier if something collapsed, if something failed. It would be such a surprise that we would radically have to then reevaluate everything we know. To me, that's a much better outcome, thinking very selfishly now, than actually confirming boringly quantum mechanics at all of these different levels, even though the picture is mind-blowing, admittedly. And then, of course, I end up speculating that we can even go beyond what Schrödinger had in mind, and maybe, and various people are making these kind of arguments, much as you couldn't have stable atoms, you couldn't have atoms bonding into molecules without quantum mechanics. Classical physics can explain none of that, and everyone agrees on this. Is it possible that even the origin of life somehow owes it to quantum mechanics? Is it possible that because of the efficiency, the speed of some of these things, which is increased in many quantum applications, could it be that life also owes it to some of these things? To me, sounds like a very fundamental question, especially that we really don't understand this at all, I would say. We don't understand how inanimate matter became alive. So these are some of the experiments that we try to do. This is a colleague of mine in Singapore, Rainer Dumke, who actually is developing superconducting qubits. And I think most of you would know, if you read the press, that actually most of industry is now betting on superconducting qubits, that they will be maybe the right platform that we can scale. Google, Microsoft, IBM, you name it, everyone is doing superconducting quantum bits. So what Rainer did is he actually put a tardigrade, a living tardigrade, on one of these superconducting quantum bits and entangled it to another superconducting quantum bit. And nothing went wrong. You could still kind of test your usual witnesses of entanglement, violate Bell's inequalities, and so on. And admittedly, this doesn't tell us really much, in the sense that it's a very crude way of probing whether quantum mechanics survives. It would be much better, of course, to be able to zoom inside, understand which degrees of freedom are entangled, and so on. But these are the first steps, I think, that people are taking to probe quantum mechanics in this domain. The tardigrade, this was a paper that was a record for biologists as well. I'm very happy about that. I always think about what can physics learn out of any of these things. But biologists were happy that these are the lowest temperatures that tardigrades ever, these are milli-Kelvin temperatures. The lowest in the past was that they were blasted in outer space. And when they returned, by the way, there was more of tardigrades than when they left. That's how robust these guys are. Not only do they survive, but they multiply, right? Now, these guys survived 1,000 times lower temperatures and ridiculously smaller pressures as well. And it was really revived. You needed to put him into a little bit of water, and he goes outside of this state of tan, as biologists call it, hibernation. So remarkable animal, but somehow that's why Rainer chose a tardigrade. And I think you're going to see a lot of these things. I will come back to it in a second, literally when I'm concluding my talk. So the final chapter was really a chapter where I revisit the foundations of physics, which we call the standard model. And I even ask questions. There are many problems with standard model. Even people who came up with the standard model said that this looks more like a heuristic set of rules. It's not a definitive final account even of the other three forces, let alone gravity. And I think I identified some interesting things that we could actually even probe in that domain. So I think even the rest of physics, even though I emphasize these hot areas and directions that people discuss, I think even in the rest of physics there are many things that we can actually learn. Let me not bore you too much with this, because we will have lots of time later also to discuss. This is because my editor, I think I had a great editor with the basic books, and my editor said, listen, it really is a physics book. It's like a love story from me to physics. And I think, as you know, Carl Sagan said that's why we communicate this. When you're in love, you want to tell the world. And I think all of these science communications come from that kind of sentiment. But he said to me, I think your readers would really be interested in what this means for us humans. What do you think would happen if all of these things happen? You walk through these portals, what happens? So I was trying to channel all those Huxley here. You know, Huxley advocated taking drugs in order to broaden our perception, right? He thought our perception is binary, discretized, but actually the world, the reality is continuous. He meant it classically. He didn't know quantum mechanics, I think. But what he wanted to say is that there might be a way of tweaking processes in our brain that really lets us see a much wider reality. And actually the last bit where I speculate about this, and I think we are on the verge of these kind of technologies, is to have some quantum chip. As you know, Musk and people like that are already developing this, but these chips are not quantum as far as I know from them. But there's no reason not to be able to manipulate them at that level. So I thought what would be much more potent than drugs is really quantum technology. And if you could somehow, first you would have to understand how our perception works, but then the question is, could you make the perception broader in some sense? I mean, this is a complete speculation, obviously, and like I said, we don't really know how our perception works, but this goes in this direction of being able to see the quantum world or understand it more directly than through this kind of mathematical formalism that we are currently using. So I think all of us agree that it's very counterintuitive, and one way to make it less counterintuitive is possibly to play with our perception. And I think that's also the future of this. So I think the book is written in the spirit that it's very exciting time for physics. Physics of the micro is leaving the confines of the microscopic world, is going into the macro world, into chemistry, biology, even maybe further into neuroscience. And I think this will define the next 3 decades of science, actually. I think this will be the way to go. And I thought this was really exciting to communicate, because something weird, something unusual may happen along the way. Thank you for your attention. Thank you. So I'm happy to answer. I think Julian said that it was okay that I coordinate the questions and answers as well. If there are any questions online, I'm also happy if you just ask me directly. So, please.
Can I get sort of
Yes.
Maybe it's just my lack of understanding, but going back to the first diagram with the three rays going off it.
Right, the alpha particle.
Yeah.
Maybe this is a direct image of the experiment.
Yeah, no, I understand. So, tell me if I got this wrong, but I'm understanding you're saying we should consider all of these, all of the molecules as quantum superpositions, right?
Yes.
And they're interacting.
Yes.
So, I've got maybe two questions there. Why aren't all the possible interactions seen? That's one thing. And another sort of variant on that is, why do we only see one of the paths of the interactions rather than
it's a great
any
question.
number of them?
Both are great, actually. They are at the, and I'm sorry for being superficial. This is entirely my fault. It's not that you didn't understand anything. In fact, I devote the whole chapter to discussing exactly this. So my argument is that in principle, you could see an interference between all of these possibilities. But what you shouldn't do then is exactly as you said. You shouldn't just put detectors at the end of each of these lines, if you like, but you must somehow be able to manipulate the whole underlying molecular gas in a quantum mechanical way, and that's what becomes complicated. So if I have only two molecules, for instance, here, and I have only these two collisions, then in fact experiments have already been done, and we know that we can ultimately quantum interfere this, and both exist. The way you explain that basically you eliminate all of the other branches, as you say, is simply due to the complexity of the situation. So it becomes irreversible in the sense for all practical purposes, because keeping track of all of these collisions and then recombining them is just an extremely difficult experiment. It's not, I'm arguing it's not an in principle problem. You can do this with a smaller number of systems, but here it becomes difficult. And the second question is the key one. You are now saying, why is it that I see one trajectory? And my answer is because your brain is also made up of Q numbers. That's the beauty that people frequently don't see. And you've got people with Nobel Prizes making this mistake, and it's very interesting. They say, wait a second, but I only see one reality. How can that be? Quantum mechanics, and Heisenberg understood this really well, almost 100 years ago. Quantum mechanics exactly tells us that you can only see one outcome at a time. If you saw the superposition, you would be violating the uncertainty principle. It would mean your brain somehow manages to sidestep the uncertainty principle. And that's Schrodinger's point. What you get is entanglement, and you get this reality in a branch-by-branch way. So each branch is a separate reality. It feels as real to the observers, if you like that name, in that branch. But you could prove that they are quantum if only really you could interfere them at the end. And I envisage an experiment of that kind in that chapter, but it's extremely difficult. So that's why these observations to us look classical, they look definitive, irreversible. It's because in the macro domain, they are for all practical purposes. But fundamentally, in fact, you should never think of them like that. That's the idea.
If we look at our brain states as quantum states, right?
Yes.
Then any one perspective generated by that brain state for an observing mind, let's put it like that, that's just one perspective. And any, if you move a few molecules in a neuron somewhere else, you might get a different perspective.
Exactly right. And that's where this is difficult to imagine. This really challenges our imagination. So I think, people call this many worlds. I think I'm a subscriber. I don't like the language many worlds because I think it still goes back to each of these worlds is a classical world. So you're almost thinking, I've got lots of classical worlds and now I put a superposition. Quantum mechanics allows everything in between as well. That's why I said the picture is much weirder than even what we communicate, actually. You could have particles that have a fuzzy position and momentum, without ever being entangled to something else. Then they could weakly start to entangle. And these branches have not even properly differentiated. Everything between 0 and infinite entanglement exists in the universe. And the many worlds is maybe this infinity, which comes naturally to us, I guess, we are macroscopic systems. But actually, quantum mechanics exists at all of the in-between levels. And that's maybe the most complete. That's why I kind of engaged in this last bit to try to speculate, maybe could we somehow get a more direct sense of what's going on there.
So the different universes are only differentiated. So the different possibilities are only differentiated by the different perspectives on it.
Yes, you could call that a perspective if you like, but again, Schrödinger would say it's enough that you created entanglement, and each of them gives you different perspectives. So you could talk from the perspective of the atom, if you like, or you could talk from the perspective of the detector or computer or measure, humans. It makes no difference. Yeah. Yeah. I think there was one.
Thank you. That was a fascinating lecture.
Thank you.
You talked about the doors of perception, and I wondered if the constraints of our minds constrained by classical physics,
yes,
are constraining progress towards
yes,
full understanding of this. Do you think there's potential for artificial intelligence or a branch of it to be developed and tutored only in the realm of quantum mechanics to think more clearly in that direction?
I love it. I love the question. It's a brilliant question. Actually, it's really, yes, I even think that the experiment I outline is, I'm advocating using some kind of intelligence simply because in that experiment you need to communicate with the person. It's difficult communicating with animals that are in entangled states, even with cats. It's difficult to get a definitive answer. But I think if you really could put an artificial intelligence there, but it has to be quantum mechanical. It really has to be made up of quantum bits. It has to be able to entangle to other systems. Then I think that would be the first test, realistically speaking, where we could really then see, is this what it means to measure something? You could then probe this intelligence and see what states correspond to this observation while actually at the higher level confirming that it's still entangled. So I think that's a fascinating question. And it leads to all sorts of other ideas that actually, as you indicated, could this improve on the evolution? Because we all agree that probably because we are macroscopic, the way we evolved is that we don't really care about these quantum corrections at our level. But maybe they do matter at some other level. It's fascinating, I think. Yeah. I think there is a mic. Yeah, that's it. Not at all.
Yeah, fantastic lecture, by the way. Absolutely fantastic. Quantum computing seems to be the real possibility here, because it uses quantum entanglement,
yes,
and may be able to do the jump that perhaps our brains can. That's my
it's
only
possible.
comment.
Yes. I think there are many speculations, exactly, as you know, that even the brain may be using quantum effects. And again, at some level, given that it's made up of biological matter, it's clear that at certain level, for short enough time, small distances, it's got nowhere else to go but be quantum mechanical. It's a bit like going into the atomic world. Of course it's quantum mechanical. That's the theory that describes that. But I think what would be genuinely surprising, what people always point out is that the brain is not like our computers. It's very delocalized. And then people end up speculating whether that delocalization could be quantum mechanical. Now to a physicist like me, this would really be very surprising. If nature managed to maintain quantum effects at high temperature, if you like, in a very messy system over distances that are bigger than a micron and times that are very short. So I think that's the discussion at present.
One final thing, then. What's your personal view on string theory in relation to quantum mechanics?
I use string theory as the only so when people say to me, what could happen in this experiment with gravity? What can happen is that quantum mechanics fails and gravity really wins. I think someone like Roger Penrose would be delighted if that was the case. I think he's almost certainly wrong at this level, but that's a difference. But that's one example of gravity winning. Quantum mechanics could win, and you might have to quantize gravity. And there are multitude, they're called canonical approaches. There is loop quantum gravity, there are all sorts of canonical approaches. And then the third option is that both are wrong. And you need a bigger umbrella theory, and these two just become special cases of that unifying theory. And to my mind, string theory is the only possibility at present. I know it's got all sorts of problems on its own, but if you're looking for an example of a theory that supersedes both and claims to have both as a special limit, then I think it's the only one I can think of. Yeah. I think there's...
Thank you, Professor, for your lecture. It was very nice. I just had a quick question. In your picture of quantum phenomena, how does the intrinsic randomness emerge? And in particular, you know, the particular, I guess, distribution, how do you account for that? And
it's an excellent question. Actually, that goes back to exactly this point of seeing one outcome at a time, seeing one trajectory in this cloud chamber, and not all of the trajectories at the same time. So I think, again, like I said, what quantum mechanics doesn't tell you, quantum mechanics tells you that when these Q numbers couple to one another, they interact, which is all there is to measurement, if Schrödinger was right about that. Then this process is completely deterministic. That's the beauty of that. We have deterministic laws that govern that. But now when you go into each of these branches, you are facing, which is your effective reality when you engage yourself and you look at the outcome here, then there isn't anything deterministic. You really are reduced to talking about probabilities. So that's where randomness comes in. If you really observe a superposition, you see one outcome. Now, I'm telling you the other outcome is real and there is someone seeing that outcome. But if you ask, but why did I see this particular outcome? Quantum mechanics cannot answer that. I would say you should phrase this the other way around. You are the person who saw that outcome later. Causality goes in a different direction. The fact that you emerge in this branch gives you that new experience that makes you different. You see what I mean? I think when you say, why did I see that, you're almost presupposing your future self as well that already exists. This one says, no, actually that's what determines that outcome. And it's completely random. And Heisenberg says it must be random, because if it could be deterministic, you'd be violating the Heisenberg uncertainty already on this object that you are. That's always the argument why you must quantize everything. It applies to electrodynamics, gravity, everything else. It's the only consistent way, which is not to say that nature will go there, when nature doesn't care about our consistency after all. But it seems to me it's an important thing to take into account. Great point as well.
In your section on the portal on time and time sort of interacting with quantum, for the experiment where you, with the quantum twins, that you have like two cesium atoms that are like entangled to radiate at the same time? Like how do you...
Yeah, that's a nice question as well. How do you do that? I think you're right. Ideally, you would be talking about one atomic clock. But then the difficulty in making a if it was really just one atom, it would be, of course, relatively easy to do that. But I think the complexity of atomic clocks is the full machinery, actually. In fact, atomic clocks are really laser clocks. What you are doing is stabilizing the frequency of the transitions inside an atom by always tweaking and correcting the lasers when you see how much of the population of this atom is excited. So there is a whole optical table, heavy machinery surrounding. We always talk about a single atomic clock, but it's not really like that. And I think what stands in the way, and I think that's why it's important that you said, would you actually be using an entangled pair? Maybe that's more realistic. to entangle two of these atoms, send one on a journey, and then cash in on that entanglement is the difference. I agree with you.
But your original idea was to take the atomic clock,
Just
put it
a
in
single,
superposition,
just a single atom. That's right.
send it on a journey in one.
That's right.
Sort of, okay,
That's
interesting.
it. Yeah.
And then if I can ask another one, when talking about sort of having them experience different directions of time, like an arrow going in one direction, how do you pull that off?
What I have in mind is really a very simple, because in quantum mechanics, we talk about unitary transformations. And then, much as with Newton in classical mechanics, it's perfectly feasible to imagine the reverse of that transformation. It's still a unitary, it's still a physical transformation. And what I have in mind is making a superposition, and you condition on the states in this superposition which transformation you apply. So in one branch you apply U, if you like. In the other one you apply U inverse, U dagger. And that's a superposition. Now you can interfere them and you can ask yourself, what does that even mean? Now, much like with the other experiments, it's easy talking about simple systems where we can do that. But can I really do that with a macroscopic or even mesoscopic system is, I think, the real question there.
Cool.
Yeah.
Thank you.
I think. Thanks.
Thank you. Thank you for your interesting chat. I'm just a little bit more draw down on the question when you have the entangled state and you, for time, and you move one away and you bring it back. How do you actually measure the clock? What's the mechanism to actually recover the element of time that the particle went away, came back, experienced?
Yes. If you, I'm going to ignore all of these lasers and everything. The simplest way is to imagine that when you put a particle in a superposition of two of its states, and let's say it's sitting in some magnetic field, what it does is precesses. And the rate at which it precesses is your clock. And so what Einstein predicts is if you make a superposition, initially they're in the same place, they're in the same reference frame, and then you take this guy on a journey, it says the precession will slow down. And when you bring it back, you can exactly see how far the state has advanced. You would use something that we call quantum state tomography. So this would require, it's not a single shot experiment, it would require an ensemble of repeated experiments, unless you time it so that the state, when it comes back, is exactly perfectly distinguishable from the initial state. We call it orthogonal in quantum mechanics. So one is pointing this way, the other one is in the opposite. Then you can have a single shot measurement, and you can show that one is younger and the other one is older. It's mind-blowing, actually. It's really interesting. So people, one comment on this. Another thing that annoys me, now this is a great opportunity to talk about these things. People say relativity talks about all of these relative perspectives, but quantum mechanics doesn't have that. Quantum mechanics is all about relative perspectives. All of these observers, the fact that I'm telling you that when you look at an object, you join different branches. If I'm outside of that, I still see it as an entangled state. Quantum mechanics is all about infinitely many compatible, amazingly enough, perspectives. And I'm going to make another strong claim. Relativity would not be correct if quantum mechanics wasn't quantum. If the world wasn't quantum, I think even the relativistic relativity would be in trouble. I know this is a strong statement, but I want to say it because usually people think relativity is going to invalidate something in quantum. But I actually think it's the other way around. It's helping relativity. Yeah. So, please. Yeah.
Thank you very much. Could I ask two practical questions? One's already an extension of what you've been talking about with qubits and trying to make chips which will actually work in the quantum world.
Yes.
I'd love to know a bit more about what you thought of that. But also, perhaps this question is completely off beam, but could what you're talking about have anything to do with improving Raman spectroscopy?
It's great. In fact, that's a great question because people talk frequently about universal quantum computers, and we know that this is difficult. I think you'd be lucky if you see 50 quantum bits that are really genuinely manipulated universal. So universal for us means you can really make any entangled state. I just ask you, make this state please, and you demonstrate to me how to do that. No one can do that. 100 qubits is certainly the limit. What we can do is improve individual specific protocols, and I think metrology, for instance, is rapidly developing for that reason. So somehow trying to do better differentiation of these quantum states, and I think Raman spectroscopy is all about that in some sense. This has a huge number of applications. But it's much easier in a way because you're not asking for a universal processing machine. You're really asking for a specific very sensitive phase measurement. And you can actually see why industry is interested in this, army is interested in this, very sensitive vibrations. How do I detect them far away? All of these possibilities. Yeah.
Thank you.
Yeah. Should I go for, you want to interrupt or one last, I think, was there one?
Is there one? Okay,
One
we'll
last
take one
one,
more
maybe.
question, and then we need to wrap up.
Okay, thanks. So I wanted to ask about your connection with Berkeley. So it strikes me that the Berkeleyan picture is also perfectly consistent, and the mystery is that we have these perceptions, and then there are objects behind the perceptions, and Berkeley wants to deny the object, and you want to deny the perceptions. So I feel like you're kind of on the same.
You're right. You're right.
And I guess one way to articulate that question is you're appealing to our perspective as macroscopic objects various times. On this picture where everything is Q numbers just in one infinite C,
Yes.
isn't it kind of self-effacing, the idea that we're these macroscopic objects that define things in relation to ourselves?
Yes, you certainly cut out a large part that, I don't think you should call that really a defining thing. In a way, I would argue that if really our perception is made up of Q numbers, then you could in principle undo even our perception. And possibly these experiments will be done maybe after AI, when we understand exactly how our perception works. You imagine, our eyes are at the interface, right? You absorb a single photon. At that point, for sure, it's quantum. Everything is quantum mechanical there. Now the guy starts to go down neurons into your brain. It's like a photodetector. Where along that line does it become impossible to conduct quantum interference? Not clear at all. So that's what I'm asking. That actually, so it's true that we probably tap into I think that's related to your question as well. We tap into an exponentially small part of reality, maybe. But I think this, if it really is quantum, then I think it would be much wider. But the final thing I want to say is that all of these philosophies are really like metaphors for us, and they help us. I fully agree with you that physics has not resolved a single ancient Greek dilemma in philosophy. Is the world real, ideal? All of these are wide open. You can argue whichever way you like. And as a philosopher, you can wiggle out of anything, as you know, right? So I fully agree that probably it's wrong to think, there are people who say, oh, quantum physics disproves materialism. Not at all. If you think of Q numbers as being your reality, they're a perfectly good example of material things. They're fluffier than what we used to think was material, but it doesn't mean you should become an idealist. That's kind of the sentiment. I think all physicists are probably realists ultimately, right? That's why you do it in a way. Thank you.
So I'm sorry, I'm casting the role of spoilsport here, but I'm only ending this part of the conversation because at the back of the room there are drinks already poured, there are books for sale, and I hope that many of you will be able to stay and carry on the conversation. So if we could just close by thanking Vlatko for a really excellent talk. Thank you.
Thank you so much.